Hello students, this is lecture number 12. Okay, so we have studied the Galerkin method in the last lecture. So in that method, a differential equation which we called strong form was to be converted to the weak form, okay, and then we had a test function ux and weight function wx, and we applied the boundary condition. Which one? The essential boundary condition first, and then we obtained the solution, obtained the approximate solution. Okay. Okay, so today we are going to study about what is known as Ris method. Okay. So here there is no requirement of converting from the strong form to the weak form, meaning that we start from something else. And what is that? So, you know, let us say a spring, we don't always have the differential equation, you know. So, there are different methods. So, let us say there is a spring and the stiffness is K and we are applying a force F. Ris method is based on something like you can also say this is based on energy method basically. So, equation we write is for energy. Yeah. So, it is not on the other hand, the for Galerkin method we use the differential equation which is strong form, and this differential equation came from the equation of equilibrium. Yeah. So, I will just write here the strong form comes from the, actually this is equation of equilibrium, or this is based on the Newton's second law. Here in this case we are going to start some sort of energy formulation. Okay. Okay. So, there is something called potential energy. Okay. So, let's call it phi x is given by strain energy. So, strain energy in this case is half k x square, or rather let us write u basically k u square minus work done F times u. So, this we have already seen this one when you were studying the solid mechanics. Yes, we had in solid mechanics we have used the energy method little bit, Castigliano theorem and all. So, this is the same thing basically. So, here the total potential energy phi x given as equal to half k u square minus f u. Yeah. So, phi is actually is a function of x. Well, x here what I mean is u in this case, right, this function of u. So, this is remember this one is u. So, this is nothing but u we mean. Okay. Okay. Now, we can if you want to solve it, how will you solve it? Okay, so we know that for this energy, potential energy has to be minimum. So solution U is such that it minimizes the potential energy. That is phi u. Okay. So that really means minimizes this one. So you can say that if phi u is equal to half k u square minus f u, then d phi over du equal to becomes k u minus f, yeah, has to be equal to 0 for minimum phi, right, and hence you get f equal to k times u, right. Okay. So this was just an example so that we can take it to the full problem. So what we see here is force equal to the spring constant multiplied by displacement, and this is what the Newtonian, it also comes from the Newton's law, right. So from same thing you can obtain directly from the Newton's law. Okay. So this that really means that we have to emphasize here the potential energy equal to strain energy minus work done. Work done is F times U, right. Force multiplied by displacement is work, and this is strain energy, means the energy stored in the spring. Okay. Okay. This potential energy itself, this one, it comes from basically thermodynamics. Okay. So this expression comes from the thermodynamics. So we are not actually going there, that is not the course here. The idea is the equation is given, the potential energy expression is given, and from there we have to solve it. Okay. Now but in this case we can write here, we know this form, that potential energy equal to strain energy minus work done. Okay. So same thing we are going to use for a bar element, something like this. So we have this, all of these things you have already done in solid mechanics actually. So let us say same equation that we solved earlier, or we can have even different one. We apply a end force F naught as well, right. Okay. And here we have B. Okay. So now for that we have to derive first. So strain energy, let us find out strain energy. Okay. So let us call it psi x equal to. So how will you find out? Strain energy will be simply we can write in terms of, so let us take one slide. So slide from here like this, yeah, and let us say this is width is dx, right. Then we have area, we have which is equal to ax, yeah. Okay. Now you can write in terms of, you know, that equal to half k u square, right, and at this point what is K? At this point K will be equal to E okay. So, so if you want to find out A will be the A is given at this section Young's modulus also we know, right. Okay. So, if you want to find out the strain energy, that will be simply we have to see what is the stress, what is the strain. So, this is the equation, it goes like this one, right. So, then we have strain here and a stress here, right, and then we can accordingly we take the area of that, right. So, simply this will be a stress times strain which will give you the strain energy, right. So, what is the stress here? In this case sigma is equal to F, whatever the force there is, right, whatever the force is at that point divided by A, right. So, this is the stress, and strain will be equal to sigma E sigma over E, right, Ex, right, or will be simply equal to Fx divided by Ex and Ax, right, that is what that will be. Okay. So, if we have to find out the strain energy, so see here, if you have a, let us talk about this point here, you have the strain, let us say epsilon, here stress is like this one, the strain energy is this, right. So, basically this is half of stress times a strain, right. So, hence our energy becomes half times a stress is Fx over A, and then we have a strain which is Fx over like this one. So, you can have either equal to whatever the stress is. So, this becomes Fa square divided by E A square. We can also write like this actually, or we can write in different form, but this is the basic like this one. Now, we are looking at this small section, right, and for that we are first we have to find out what is the normal force here, okay, and then we have to divide it by area and Young's modulus like this one. Okay. So, this we can also write, this is equal to half, and this sigma. So, we are writing in now the convenient manner, so that we can also have the some kind of derivative as well, you know. So, this is a continuous system. So, there will be the sigma, this has to be true for the whole beam, for the whole bar, right. So, we can write this stress as equal to E times, as we know that sigma equal to Young's modulus times a strain. So, half E strain square, right. So, we know that strain energy also of this form, and is equal to half E can vary along x, right, and then we have du over dx square, right. Okay. So, finally, what we get, what we got so far, this one is the strain energy density, right. So, This is strain energy density, which is given by half like this one. So, total strain energy, for that we have to somehow we have to integrate. How? So, this one is at every point. So, we have to multiply by volume, right. So, volume is Ax multiplied by dx, right. So, what do we get? We get total strain energy, strain energy for the strain energy for the for what? For this section, for a small slice, right. For this will be equal to, for the small slice, right, or let us call it d psi will be equal to half E x du over dx square multiplied by Ax multiplied by dx, right. So, this is total strain energy for the small. So, this is the strain energy for the small slice, and similarly you can write total strain energy, total strain energy for the bar, right. Will be psi is equal to this, okay. For the whole domain, B is equal to, we can write, since this is x is given, so we are going to 0 to L, and it will be half E x A x, right, and then you have du over dx square dx, yeah. So, this is the total strain energy for the bar you get, okay. Now, we have to find out the work done. So, what is the work done? Yeah, so that we can write that. So, work done. So, we have there are two kinds of forces. One is the body force here that you are seeing. So, this is Bx here, and then you will have U, that is the displacement here. So, force becomes B times U, yeah, and remember that this B is the force per unit length, yeah. So, total force will be Bx times dx and then multiplied by U. So, for the small element, this one, for a small slice, you will have the, we can, let us write. So, work done by the small slice, okay. So, let us write dw will be equal to Bx multiplied by Bx multiplied by dx, okay, and multiplied by U, whatever the value of displacement is that, right. So, say total work done by the small slice will be equal to, let us call it W1 is equal to dW is equal to, again it has to be integrated over the whole length. So, 0 to L, and then you will have Bx times Ux multiplied by dx, yeah, okay. So, this is one part of the work, because there is also a force at the end as well, right. So, if not, we have applied. If there is no force at the end, then we can, then there is no need, but if there is a force here, we have to apply that too, okay. And that will be simply U F naught multiplied by whatever the value of displacement is at that end, right. So, okay. So, also I write the length is L, okay. So, for the work done by this end force will be equal to F naught multiplied by U at L, right. This will be the force, right. So, we can write that. So, So let's add work done by the concentrated end force. Okay, so there's W2 will be equal to what? F naught multiplied by U at x equal to L. So this is what the force is. Okay, now we have the strain energy, we have the work, and we can now put write the equation. So what equation we have? So we know that potential energy is equal to strain energy minus work done. Okay, so we have like phi x equal to strain energy, which is psi x multiplied by, there are two work W, or is equal to where W equal to W1 plus W2, yeah. So equal to W can also be a function of x, yeah. So we write it is like this, okay, where we have psi x we have found out 0 to L E x A x du over dx square, or there will be half also, and dx, right. So this we have, and then we have minus W1. So W1 is equal to 0 to L, and then we have Bx, right. So force per unit length multiplied by dx multiplied by ux, and then dx. Okay, so this is what that will be, since B is the force per unit length, yeah. And then we will have second W2 will be F naught multiplied by U at x equal to L. So this is what the potential energy is. Okay, now this equation basically equivalent to the strong form that we derived earlier, right. So this is equivalent to which so this is just this energy based, and the other one is the force based, that's the only difference. So this is equivalent to what? Remember we had d over dx E A, then d u over dx plus b equal to 0, plus boundary conditions, plus we have the boundary condition here, right. So this is equivalent to this equation, yeah. But if you compare, what you see here is in this energy based equation you have just single derivative of u here, but a squared. But in this case we have the double derivative of u. Hence the requirement, as you can see here, the potential energy already in the form that it can take a linear solution already, right. You can take the linear solution here, but this cannot take, and hence you have to transform this into the weak form, right. But in this case in the potential energy based formulation, du over dx is there is no ds square u dx square, that is there is no double derivative of u. Hence we can easily take the u as a linear, we can solve it, yeah. So let's solve it and find out how it is. Okay, so basically remember that for the Ris method we are going to start from the potential energy format or something like this one, right. Okay. Okay, so let's solve problem. So let's solve the same problem as we solved earlier, and let's see the how it looks like. So earlier problem was we had a constant b, right? B naught, b equal to b naught, and then a equal to a naught, all constant, e equal to e naught, right? Like this one, and then we had ux equal to 0, and there was no force, so f naught equal to 0, right. So because our equation has f naught, so this is 0 anyway, so that we can put also later on, or maybe let's solve it with the f naught, some value f naught. Okay, so we can put in the answer we get we put f naught equal to 0 and see, and we'll get the same solution as we get earlier. Okay, so this also gives you the another example where you have the force acting at the end. Okay, so it's good. Now how are we going to solve? Okay, we will start the test function here also. Here test function means approximate solution we are going to find out. So assume solution which u x equal to, like we did earlier, alpha x plus beta. Okay, now first we have to, what we have to do, we have to apply the essential boundary condition to begin with. Okay, so how are we going to do? Apply the essential boundary condition, and hence what we will get? We get alpha u x equal to 0 or u 0 equal to 0 plus beta equal to 0, hence beta equal to 0. So our solution here is ux equal to alpha x is the solution we are going to take. Only thing is we don't know what is alpha, right? Alpha equal to what, that we don't know, and then we are going to solve it. Okay. Now if that is the case, then we can have the potential energy. Okay, psi x we can write it now, and psi x is will be 0 to L, and then we have half, then e naught, right, a naught, all constant, then du over dx square, right. So du over dx, and in our case du. So if we have of this form, then we know that, so du over dx equal to alpha only, right. Okay, so we can make use of that, right. So we will have half d over dx is a square of that, so we have alpha square, right, and then we have half, that's it, then we have dx, right. Okay, then we have w1 we have u, so 0 to L, then we have v naught, and then u is nothing but alpha x, so we write alpha x dx, and minus we have f naught times alpha, f naught times u at L, u at x equal to L, but u itself is alpha x, right. So if u x equal to alpha x, then u L equal to alpha times L, right. U L is equal to alpha times L, hence we will put, simply we will have f naught multiplied by alpha L. So this is what our solution, this is what our potential energy is. Now here if we see what is the variable, we want to minimize the potential energy. Typically we want to minimize with respect to u, right. Here u itself is a function of x and alpha, right? And x varies from 0 to L. This is a variable. Only thing, whatever the constant there is alpha. So that really means we have to minimize the potential energy with respect to alpha, right? So alpha is the variable that we have to optimize so that we get the minimum potential energy. Okay. So we write for minimum potential energy, okay, what do we have? The condition is d phi over d alpha has to be equal to 0. Yeah, and this tells us what? This tells us that first of all, we can integrate it. There is no x term here, so simply it will be multiplied by L here, right? So we can also integrate and also differentiate with respect to alpha as well. So we can write half E naught A naught L. So half E naught A naught and L coming from the integration, right? And then we have alpha square. Alpha is not a function of x, this is a constant. So we are going to differentiate as this one. We are with respect to alpha. So we get 2 alpha, right? So multiplied by 2 alpha minus, okay. See here now. We can differentiate alpha, so d alpha over dx, d alpha over d alpha, so 1. So simply this will be b naught times x dx. So this will be simply b naught times x square over 2, and then limit L to 0, right? Okay, and then we have in this case we just have a differentiate of this one, so f naught times L. So f naught times L, yeah, has to be equal to 0. Okay, so what you see here, alpha is just here. There is no alpha here. There is no alpha here. So we get the value of alpha. So basically, or we get E naught A naught L alpha is equal to B naught L square over 2 minus F naught L. Yeah, and or alpha is equal to, we can have L common, so L cancels out, so B naught L over 2, so B naught L over 2 minus F naught divided by E naught A1 divided by E naught A1. Yeah. So the solution is Ux equal to alpha x equal to B naught L over 2 minus F naught x over E naught A naught. Yeah, so this is what the solution we got. So this is the solution. Yeah. Okay. However, we solved earlier with f naught equal to 0. So when f naught equal to 0, Ux will be equal to 0, put 0 here, and we get simply half B naught L over E naught A naught times x. Yeah. So which is similar to the solution we got last time. We get exactly the same solution. Yeah. And hence we get U at L is equal to half B naught over E naught A naught L square, right. So, this is what you got, and which is the exact solution when F naught is equal to 0. Yeah. Okay. So, this is what you call the Ris method. Okay. Here we also try to here it is very easy to relate to in case of a structure, because this has potential energy. Yeah. However, any differential equation, the boundary value problem, can be written as this energy, right, like something like this expression, something like this expression, you know. Yeah. So, this is one of the ways to also solve the problem. So, this is also solving the same problem, but different method. Okay.